Hello everyone, welcome back to one more session on multisim. Here I am going to demonstrate the simulation of log amplifier. Uh, I did not want to waste any time, so I have directly taken the circuit of log amplifier. I have already constructed the circuit of log amplifier where I am using a inverting amplifier using Opamp. I am using a 741 op amp in inverting mode where R1 is taken as 1 kilo ohm. In place of the feedback resistance RF, I am taking a diode. Okay. In place of feedback resistance, I am taking a diode. To the R1, I am connecting a DC supply of say 12 volts. Of course, it is not compulsory that it is 12 volts, so we can change the value. Of course, we are going with the DC sweep, so whatever value you take for this V1, it doesn't matter. Plus VCC at pin number 7, minus VEE at pin number 4. These two voltages are given, and output is taken at pin number 6, measured using multimeter. When I click on the multimeter, I am measuring a DC voltage. So this is regarding log amplifier. And coming to the basic theory part, log amplifier is the amplifier whose output is proportional to the logarithmic of input. Output is proportional to logarithmic of input, which is natural logarithm. Say whatever current flows through the resistance R1, the same current flows through the through the diode. Okay, because op-amp draws no current, whatever current flows through the resistance R1, same current flows through the diode. This is the basic concept. We know that the current flowing through the diode is ID is equal to IS, where IS is the reverse saturation current, into e to the power of VD, voltage across the diode, where in this case it is feedback voltage VF divided by eta VT, where VT is the temperature equivalent voltage, minus 1. So please don't mind me typing it in an odd way. E to the power of this entire thing should be in the numerator. V suffix t. This is V suffix t. This n is I am writing it as n instead of eta because I cannot take symbols here. So reverse saturation current multiplied by this is diode current equation. Of this diode current equation, usually Vf is the forward voltage of the diode, which is usually positive. So e to the power of some positive voltage is always far greater than 1. So this one can be negligible, and I am removing this one from the equation. And temperature equivalent voltage will be 26 millivolts at room temperature. So I can change this to 26 millivolts. Also, eta value in different textbooks, different notations, the authors are giving different versions where its value is between 1 and 2. Say in some textbooks it has been given that eta value is 1 for germanium and 2 for silicon. Some people say that eta value will be 1 for using the diode as an individual component, and 2 when it is used for used as a fabricated component. So different versions are there. So for example, let us take 2. 2 into 26 will be 52 millivolts. Right? Directly, let us avoid all these things. Let us avoid more parameters here. So ID is equal to IS into e to the power of VF by 52 millivolts. Right? From this, if I equate here, I is equal to input voltage minus potential at this node 1. V1 minus the voltage here is 0 because it is virtual ground. V1 by resistance R1 will give you the uh, current here. So V1 by R1 is equal to this diode current equation. That is how we can get the equation, and by simplification you will get output is equal to output is equal to minus eta Vt into natural log of uh, V in divided by uh, reverse saturation current Is multiplied by R1. That will be the final equation. Like V out is equal to minus eta Vt into natural log of V in divided by Is into R1. This will be the final equation, where you can see V out is directly proportional to the logarithmic of input. Okay, this is the theoretical part roughly. Let us see how we can simulate it and how we can interpret the results. Say for example, if I am taking this V1 as a 2 volts, I am taking this V1 as 2 volts and I am running it. You can see the output is minus 586.298 millivolts, or approximately minus 587 millivolts. And you can clearly see that the current here I is equal to 2 milliamps, and the feedback current I is also 2 milliamps. No current is drawn through the op-amp. Same way, if I change this value to say 5 volts, it says that since simulation is running, it will do the process after stopping and running the simulation again. So I will stop it and run the simulation again. You can clearly see the value has changed here, minus 629.263 millivolts. The current is 5 milliamps here through R1, and the current through the diode is also 5 milliamps. Now uh, let me delete this so that I can avoid the confusion. Let us do the DC sweep, where I vary the input voltage from 0 volts to say some 15 volts, or 0 volts to 10 volts. Go to simulate, analysis and simulation, go to DC sweep. Once you go to DC sweep, it will show sources. Since you are having only a single source, uh, VCC and VAE are voltage sources which are connected for the power supply purpose. Now you are applying the input through this DC source V1. So choose V1 here as source 1. Start value, let it be 0. Stop value, let us take it as 10 with an increment of 0.5. Okay, 0.5 or 0.1 or 0.01. Since it is simulation, you can take any number of samples in between. Okay, and now go to output. If you observe here, the output will be V2. So choose V2, add to the output variables, selected variable for analysis, and run the simulation. See, this is how we are getting our output. Let me change it and okay, this is how we get the output. Whether this output is correct or not, for that what we have to do, we have to go with the differential uh, output voltage, which we have to verify whether it is following the logarithmic value of input or not. So you take the cursors, you take the cursors. There are two cursors here. Red one is cursor 1 and the blue one is cursor 2. Say I will take cursor 2 at 2. Okay, cursor 2 at 2, and let me take this cursor 1 at 1. So you can verify on x1 is 995 and x2 is 1.99, which is approximately 2. Since I am moving the cursor manually, exact location is slightly difficult. Now what is the difference between these two? Now this should be voltage v1 and this should be voltage v2. Difference between these two should be equal to logarithm of v in 1 by v in 2. Okay, v in 1 is 1 volt, v in 2 is 2 volts. Logarithmic of 1 by 2, log 0.5. That is the value which we will be getting here, and that value is here represented as dy minus 32.4755 millivolts, or in volts minus 0.032 millivolts. That will be the voltage. And now if I take this trace, export to Excel, here an Excel sheet is created, and usually we see that v1 value is this one. Let me color it, and at 2 volts this is the value. Okay, difference in the outputs, let us measure here. Let this will be v out 1 and this is v out 2. Fine. Now v out 2 minus v out 1 is equal to this value minus this value, which is minus 0.03247, right? Minus 0.03247. This is the value we got here. So this is how we can verify logarithm of the difference of these voltages. That is what we have to verify. Thank you very much. Uh, Thank you very much for listening to the demonstration thoroughly. Let us meet in the next session with anti-log amplifier. Thank you.